So today's lecture will be devoted to a proof of the splitting principle. Last time we applied it to prove that in a certain situation the Euler class is the same thing as the Chern class, and we have seen that it came very conveniently into the game. Basically, the principle allows you to, whenever you want to prove a polynomial identity of two characteristic classes, then it allows you to assume that the bundle that you're considering splits as a line bundle into line bundles. And in general, that's not true, of course, but you can pretend it, and you need only to prove your statement in this situation. So, the splitting principle, I'm going to reformulate it. So the aim is to prove the following theorem, which we used last time. So let's consider a complex vector bundle. It has C. Let's say vector C bundle on a manifold M. Then there exists a smooth manifold Q and a smooth map, differentiable manifold, and a smooth map I from Q to a higher base manifold M, such that the following two things are true. First of all, if I pull back my bundle along this map, then I get a vector bundle on Q, and this bundle on Q splits into line bundles. Where the LJ line bundles are vect 1 C bundles. And secondly, the cohomology of M embeds into the cohomology of Q under pi. So map pi from the cohomology of M to the cohomology of Q is injective. And this is what we used, right? So we wanted to prove certain identity of characteristic classes. Then we just pulled back the bundle that we were considering to such a manifold Q. There it does split into line bundles. Then we prove the identity over Q. And since this projection is injective, the corresponding identity also holds on M. So this is how we use it. It's a very general principle that's often useful in the theory of characteristic classes. Okay. And in order to see how to get this manifold Q, this map pi, we will first sort of discuss the second issue here, the cohomological issue. And so homological class first. And this is another theorem which is useful in various contexts, and so it's nice to see it anyway. So that's a theorem by Leray and Leray-Hirsch, Leray-Hirsch theorem. And this gives us a condition under what circumstances, if you have a fiber bundle over a manifold, under which circumstances we can compute the cohomology of the total space of the fiber bundle out of the cohomology of the base and the cohomology of the fiber. In particular, that we will see under which, that in this case, this is an injective map. So let me formulate it. So now since this is a completely different bundle than this one, let me call it differently. So let G be a fiber bundle on M, on manifold M, And now I need to give the total space and the projection a name. So with total space E and projection let's call it P from E to N. So it's no longer a vector bundle, it's just some kind of bundle. And now the assumption is, suppose that there exist cohomology classes A1 or AJ in H AJ of the total space, J running from 1 to n, let's say, such that whenever I restrict the cohomology class to a fiber, then this will be a basis of the cohomology of the fiber. So such that if this inclusion, so that Ix is the inclusion of the fiber at the point X into the total space. Remember, the total space is just a disjoint union of fibers. So let's look at this inclusion map. And now I can pull back these forms or these cohomology classes to the fiber. Then these give me cohomology classes of the fiber. And I assume that these restrictions to the fiber give me a basis of the cohomology of the fiber. So this form a vector space basis of the cohomology of the fiber for X. So this is the inclusion. So that's the assumption. And what's the statement? So in fact, if this is true for some X, it's true for all X's, at least if the basis is connected, because the fibers are all diffeomorphic, so they have all the same cohomology, and which fiber I take here for my inclusion doesn't play a role. So if you have if M is connected and you have two different points here, then the corresponding iotas are homotopic to each other. So this gives a basis for one X, it also gives the basis for all other X's. Anyway, so and then the conclusion is this, then the map theta going from the direct sum, I write it like so, take the cohomology of the basis, tensor with the cohomology of the fiber, and map it to the cohomology of the total space. The map is given by taking an element here, tensored. So here, for this space, we have a basis, namely these elements here. So any element in the tensor product can be written in a unique manner as a sum of these basis vectors as a second factor and some vector from that space, the first vector. So I can write them as Bj tensor iota x star of aj. Right, each element in the tensor product is of this form with unique Bj's, and this map to the sum. And now I take this cohomology class in Hm and pull it back to the total space using my projection map. So I take P star of Bj, and then I take the cut product. So this is a cohomology class in E, and the A's are also cohomology classes in E, so I can take the cut product and so on. Okay. And then this map is an isomorphism. Then theta is an isomorphism, where this is the theta. So that's the statement. So the n is just related to the dimension of the homology of the fiber, which is unrelated to any of the dimension of the manifold. All right. Before we prove it, let's discuss it a little bit in some examples. Usually the trivial bundle is not an interesting example, but in this case it actually is. So let's look at the trivial bundle. G trivial bundle with model fiber G. So that means the total space in this case is just the product of M, this model fiber, and yeah, the projection map is just a projection of the first factor. And let's see if we can check the assumption of the theorem. So we need to get somehow these AJs, which are homology classes on this product. How can we do that? Well, let's start with the homology of the model fiber. So let alpha j in homology of the model fiber be basis. And here, in fact, since I formulated it here, so I assume that these are finitely many. So I assume that the total homology of the fiber is finite dimensional. This is automatic if the manifold is compact, for instance. But you can have manifolds with infinite dimensional homology. If you have something like a surface, which is an infinite ladder going to the left and to the right, this has infinite dimensional homology. So this is something I want to exclude here. I look only at the case when G has finite dimensional homology. For instance, if G is compact. And that's also the situation we will meet later when we prove the splitting principle. So let's say G compact for simplicity. Or more generally, the homology of G is finite dimensional. Okay, and then if this is finite dimensional, of course I can pick a basis. The basis where they are homogeneous, so the alpha j's are in HKJ model fiber. And now, in the trivial case, I do not only have the projection on the base manifold, I also have the projection of the fiber. So let's look at that. Q, E to G projection in the second factor. And then I can use this projection to pull back these homology classes product. So let me put AJ to EQ star alpha J. Now I have homology classes total space. And so let's see, we have to check that if I restrict it to one of the fibers, then I get a basis of the homology of the fiber. So what's going on here? So if I have a fiber Gx, which is nothing but x plus model fiber in this case, and so I can get it into M cross G, which is my total space. Then I can go and project back onto the second factor. So what will happen then? Well, then x comma G will be mapped to x comma G will be mapped to G. And so this is just, so that's obviously a diffeomorphism. And if I now apply this to my AJ, which is nothing but Q star of alpha J, is the same thing as Q composed of X star alpha J, we see that the spaces of G gets mapped by this diffeomorphism to a basis of Gx. So that map here is composition is a canonical diffeomorphism. And so therefore the basis alpha J gets mapped to a basis Gx. Alright. So this is okay. So in this case, in this situation, we can apply the theorem. And now, what does it tell us then? We have this isomorphism. So I can apply Leray-Hirsch. Which gives us that the homology of the base manifold tensor homology of the one of the fibers, which is of course the same as the homology of the model fiber. And this maps isomorphically to the homology of the total space, which is just the product of the two. And what's the map? Well, we have some B here, tensor some element here. And then what do we do? So this one is pulled back using the projection on the first factor. And this one is pulled back using the projection on the second. That's an isomorphism. And in this particular situation, this is known under a different name. You may have seen this before. So when you have, so here we have computed the homology of a product manifold, which is nothing but a trivial one. And there's a famous name associated with this. And you're now thinking, oh, yes, I remember that, but I just don't get to the name. It's known as the Künnert formula. So in this sense, the Leray-Hirsch theorem is a generalization of the Künnert formula. Künnert formula is the case of a trivial bundle. Okay, so this is a situation where the Leray-Hirsch does apply, but there are lots of bundles where these assumptions are not satisfied and where the conclusion is also false. So let me give you an example. So the remark, there are lots of bundles where the statement, where the assumption is not satisfied and the conclusion is also false. For many bundles, assumptions in Leray-Hirsch are not satisfied. For example, well, what comes to our minds? So which bundles do we know? We know the Hopf bundle, so let's take a look at that. Or, yeah, Hopf bundle, which is the circle bundle associated with the tautological line bundle. In this case, the base manifold is CPN, and the fiber is S1, and the total space. So what's the total space in the Hopf bundle? It's so that's the bundle that you get if you take the tautological line bundle, which is a complex line bundle, and you just restrict to the unit vectors of the tautological line bundle. Right? Then the fiber is no longer C but S1, and also total space. What's the dimension of the total space? It's the dimension of this one plus the dimension of that one. So this is real dimension 2n, this has dimension 1. So it must be something 2n plus 1 dimensional, right? Yes. Maybe we should take a look at the lectures in the beginning, where we discussed this bundle. So that's the Hopf bundle. Because the tautological line bundle arose like this, you take the trivial Cn plus 1 bundle, and then you take the one-dimensional subspaces corresponding to the points in here. And if you restrict to unit vectors, then you restrict to unit vectors in Cn plus 1, which is this. So that's why this is how it looks. And now let's take a look at the homology. So in particular at the dimension. So the dimension of the homology of this guy So what's the dimension of the homology of Cpn? We have computed the homology of Cpn. N plus 1, yes. Because remember, so it has homology in degree 0, 2, 4, etc. And the homology is spanned by the German class and its powers of the tautological line bundle. Yeah, this is what we have here. Now the dimension, that's the homology, sorry. Homology, space itself. For the space itself, it would have been 2n. Now the dimension of the homology of S1 is what? It's the sum of the Betti numbers, right? So the Betti numbers are the dimensions of the individual parts of the homology. So what's the sum of the Betti numbers for S1? Should be 2, yes. We have something in H0 and something in H1. And the dimension of the total space, which is S2n plus 1, is what? How does the homology of the 2n plus 1 sphere look like? Yes, it has homology in which degrees? And in 2n plus 1, right, in the dimension. And so we see that if we take basis, the dimension of the basis, or homology of the basis is n plus 1, the dimension of the homology of the fiber is 2, and the dimension of the homology of the total space is 2, and that is not the same thing. So certainly the tensor, that would be the dimension of the tensor product, so the dimension on the left-hand side, and this is the dimension of the total space, so it's on the dimension on the right-hand side. So they don't even have the same dimensions. So certainly this isomorphism thing does not hold, the conclusion does not hold. So conclusion does not hold. And therefore, the assumptions can also not be true if we believe that the Leray-Hirsch theorem is true. And so, let's see, where's the problem sitting? We have this total space here, and we see on the total space, we have non-trivial homology only in degrees 0 and 2n plus 1. But in order to have that, we would need, so the fiber is S1, and so that has also something in degree 1. So we would need a homology class on the total space in degree 1, which restricts to something non-trivial on S1. But the first homology of this one is 0. There is nothing non-zero. So if we restrict that to the fiber, we also get 0. So we cannot produce something in degree 1 here on the fiber. For degree 0, it's okay, because degree 0, we have the homology class represented by the constant function 1, which restricts, of course, to the thing represented by the constant function 1, which generates H0. H0 is okay, but H1 is not okay. So that's why the assumptions are not satisfied. And as we see, the conclusion is also not true. So one could say the Leray-Hirsch theorem applies whenever the bundle is not too non-trivial. So it does apply if the bundle is trivial, and it does not apply if the bundle is very non-trivial and the Hopf bundle is already too non-trivial for this one to apply. So we don't find these HJs anymore. But there is also a range of bundles which are non-trivial, where this statement is still true, so that we still have the same formula for the cohomology as for the trivial bundle. However, one should say it's only a vector space isomorphism. So I'm not saying anything about the ring structure of the cohomology here. Remember, the cohomology is a ring, and so we have a ring here, and this theta is not a ring homomorphism, it's just a vector space homomorphism. So I'm not claiming that as a ring, somehow this can be written as a tensor product. Okay, so these are some examples, and now let's prove it. I mean, here's the first. So, there we have it. And in fact, the proof of Leray-Hirsch and I will deal, so it holds in this generality. I will look at a somewhat more restricted case, namely, I will only do it for bundles of finite type. For Leray-Hirsch, if the bundle, this bundle is called G, is finite type. What does that mean? That means there exists a cover, a finite cover, U1 all the way up to UN of the base manifold, such that the U's and all non-trivial intersections of the U's are all diffeomorphic to Rm, so they are all orthogonal, such that U1 up to U of k is either empty or diffeomorphic to a ball or to Rm, where m is the dimension of the manifold. So this is a finite open cover. That's one thing, and then I want to have that the bundle is trivial over each of these UJs. In fact, this is automatic, but it doesn't matter. So, and G is trivial over H in general. So manifolds always have this kind of open covers with this property, but in general it's not a finite cover. It can, in the compact case, of course, you always can, you just take some good cover and then take a finite subcover. So in the compact case, this is certainly satisfied if the manifold M is compact. In many non-compact cases, it's also okay, for example, in Rn itself. But in general, that's not always the case, like the example that I mentioned earlier with this surface of infinite genus, then this will not work. The statement is still true, and also we need this only to make sure that a certain induction can be done. It's not really crucial to have that. And you can, the argument that I'm going to give is based on the Meyer-Vietoris sequence. This can be organized in a different manner, and this Meyer-Vietoris argument that I'm going to give, and then it's called the spectral sequence argument. But I don't want to get into these formalities, so that's why I want to stay more elementary here and just make this assumption. But anyway, if M is compact, for example, then this holds anyway. All right, now how do we prove that? And well, we will try to go from local, where things are trivial, to global. So for any U in M open, we write theta U for the corresponding isomorphism, hopefully isomorphism for the corresponding map that I have here, when I restrict everything to U. So that means it's a map from the cohomology of U rather than M, tensor the cohomology of the fiber. So X should be point contained in U. 2. Well, and on the right hand side I have to take the bundle which I get by restricting to U. The total space of the bundle restricted to U. So that would be the pre-image of U if P is the projection map. So that's a subset, an open subset of E, the total space of the projection map. And same map, right? So the same map, so sum of Bj tensor U star X Aj. These are the fixed Aj's. Is being mapped to some pullback of Bj, cup product with. Now I'm not just taking, I have to take alpha j, Aj, but this is something on the total space E itself, so I have to restrict it to this pre-image. So let me write this as iota of the inclusion map of U into M, or rather e to the minus 1 of U into E. So whenever I write something like I of x comma y, I mean the inclusion of x into y. So that would be the general. We'll have to look at lots of inclusion maps, so this will be the general notation. So basically this is the restriction of the AJs to this subset. So this is just the corresponding map for this bundle restricted G. It's a notation. And now we will start by arguing what happens if U is in fact diffeomorphic to Rn. So in particular this applies to if U is one of these UJs up there or one of these intersections. That's the first part. Okay, so let's look at the case and consider the case when U is diffeomorphic to Rn. So what happens then? Well, in this case, let's look at this map. U, what will happen? So this maps H star of U tensor H star of fiber to H star, the total space restricted to U. Now, since U is diffeomorphic to Rn, there's not a lot of homology surviving here. Then we only H0 survives, and that's isomorphic to this guy. This just consists of the H0 part, and that's isomorphic just to R. By the homology class represented by the constant functions. Yes, U is diffeomorphic to Rn. And so the whole thing is then canonically isomorphic to R tensor dx, which is of course nothing but H star dx. that's the left-hand side of the picture. And the right-hand side, here we have a bundle, and this is trivial over contractible set. So this will be isomorphic to H star of U cross the model fiber or Gx, because the bundle is trivial. But now this is Rm, so this one is still homotopy equivalent to Gx because U is homotopy equivalent to a point. So you take the homotopy equivalence from U to a point, cross the identity of Gx. And so this is the same as homology of Gx. Now that looks good because now we see on the left side and the right side we have basically the same space. And what does the map do? Well, we have to take such a tensor product now under these isomorphisms. First, we have identified this H0 part with R, so we can, under this identification, these BJs are just real numbers. Right? Under this identification, these are real numbers. And so this gets mapped to, so I could also leave out the tensor product here if I wanted. And so under this identification, this just means I have to remove the tensor product sign here. So this corresponds under these identifications just to sum of Bj times Ix star Bj. So when I consider the element up there as an element in there. And so this is getting mapped to what? To the sum of P star Bj cut product with I star Aj, where over here we have the inclusion the inclusion of Aj to U. Okay, and in fact, since these are here in this picture, they are just real numbers, I can also write this as by linearity of I star. I can also write this in this way. Simply by linearity, I can put in and pull out coefficients. So that's what I have here. And here, okay, so I have, this is when I consider the element in here. Now under these isomorphisms, what happens? Well, the isomorphism, this homotopy equivalence is just given by the inclusion of this fiber into that product. So that means if I take here this isomorphism, then this means that instead of the inclusion of the whole thing into E, I look at the inclusion of the fiber into E. Of J. Now, these Bj's are considered just as real numbers, so P upstairs of Bj is also the same real number. And then the cut product of a 0 degree class, which is a real number, times something is just the usual product. So I can just write a dot and sum of J. Okay? Yeah, and then obviously it's the same thing. So meaning under these natural identifications that I have made on the left-hand side, where I got this space, and on the right-hand side where I got the same space, under these natural identifications, the theta u is just the identity. So it is an isomorphism. Therefore, theta u is an isomorphism. Okay, so that deals with the situation when I have a trivial bundle over one of these special sets. Now, this applies in particular to each of the UJs and also to each of these intersections. And in order to get to, I want to keep this, in order to get to the whole manifold, what we now do is we will prove that if we have two open subsets of the manifolds, for which the theta u is an isomorphism, and over the intersection is also an isomorphism, then we conclude that it must also be an isomorphism for the union. Once we have that, we can use the fact that we have this cover, because then we know it's an isomorphism on U1 and U2, and also on the intersection. Therefore, it will be an isomorphism on the union of the two. We also know it's an isomorphism on U3 and on the intersections, and then we can conclude that it's an isomorphism on the union of U1, U2, and U3. And then at some point this will stop, and this is where we need this finite type assumption that this procedure stops at some point. And then we know that it's an isomorphism on the whole manifold. Okay? So let me write this down. Well, that's the second part of the proof. Remains to prove, remains to show if theta u, theta v, and theta u intersect v are isos, so is theta u union v. Now let's see how we can do that. And this is where the Meyer-Vietoris sequence comes into play. So let me write down the Meyer-Vietoris sequence. So for these subsets U and V, so we start with the union, which is what interests us. Then we get to HK of U plus HK of V. Leave a little space here. So the sequence will be pretty long, with more space here. Then we go to HK, the intersection. And then we have a connecting homomorphism that gets us to the next level, HK plus 1 of U union V, and so on. So that's the Meyer-Vietoris sequence. And this is exact. What are these arrows? Well, the map from here to U is just the restriction to U. The map from here to V is the restriction to V. So it's just taking the restriction to U into the restriction to V. The map from here to there is both the restriction to the intersection, here and there. We have to fade in one minus sign at some point to make sure that the composition of these two maps is 0. Doesn't really matter where we put the minus sign, but there's one minus sign to be added for that. And then there's a connecting homomorphism from here to there. And how does that work? So we take a cohomology class in the intersection, which is represented by a closed form. Then we extend this form from the intersections to U somehow, and also from V to from the intersection to V somehow. and take their differentials. On the intersection, this will give you the same thing, namely 0. Then these differentials can be put together to give you a form on the union. And on the intersection, they coincide at 0, so that's why it patches together in a well-defined manner. And since it's locally always a differential, it's an exact form which represents a homology class. So that's how the connection homomorphism is used. Just to remind you. Okay, so that's an exact sequence. And now what we can do is we can take a cohomology of the fiber and just tensor with it. So we take one fixed vector space, which happens to be the Lth cohomology of the fiber, and we tensor everything with it. And we extend the arrows by identity on the second tensor vector. Then this is still an exact sequence, right? If you have an exact sequence of real vector spaces, you tensor everything with one fixed vector space and extend the maps by identity on that fixed vector space, then this gives you another exact sequence. So that's still exact. And now let's not do this just for one choice of L, and K is increasing here, but let's do this here. Take the direct sum where for K plus L adding up to some fixed degree, which I might call, I don't know, M and N I think I've taken already. So let me call it P. No, P is the name of the projection. U. So I sum over all, I do this not just for one L, I sum over all these L's, and I have here the same sum. A plus L is equal to U. Similarly here. A plus L is equal to U. And here, I also have sum of K plus L is equal to U. Or I might now rename this K plus 1 to be K, and then this adds up to U plus 1. And so on. So basically I've taken exact sequences for each L level, and I just sum them. And if you take the sum of exact sequences, then you get again an exact sequence. So this is still an exact sequence. So that looks already better, because now we are getting close to what we have on the left-hand side here, right? So we have so what we have here, for this one guy here, we have the muth degree of this space when M is the union. Here we have the muth degree of the space when M is the intersection. And here we have, that is the same thing as writing the muth degree of the first one. Tensor that one, plus the same thing for this guy, using this associativity of the tensor product. So that means I have the sum of this guy, muth degree, and this guy for U, and this guy for V, muth degree. So so the left-hand side for this isom theta map is popping up here for different choices for M. For the union of U, for U and V, and the intersection of U and V. Alright, good. And so that's an exact sequence because of Mayer-Virturis. And now we can play the same game of Mayer-Virturis also on the total space side, where I use the open sets which are given as p to the minus 1 of u and p to the minus 1 of v and the union and the intersection. Okay, write down another exact binomial sequence, which will be h mu of p to the minus 1 of u union p to the minus 1 of v. And here we have h mu of p to the minus 1 of u plus h mu p to the minus 1 of v. Here we have h mu of p to the minus 1 of u intersect p to the minus 1 of v, and so on. So that's also exact. That's an arbitrary sequence on the total space. It's also exact. And so we can rewrite this as h mu of p to the minus 1 of u union v, and here we can rewrite this as h1 minus 1 of u intersect. In three images commutes with intersections and unions. And now what we see is now we always have the right-hand side of the theta map if we replace the manifold M by either the union or by u or by v or by the intersection. So we have these two exact sequences, and we have also these theta maps between them. So let's add them to the diagram. So we have the theta map here, restricted to the level u, which is associated with u union v. Here we have theta u plus theta v. And here we have theta u intersect v. And here again we have theta u union v. Now on the next level u plus 1. And so on. Okay, so we have this big diagram. So we have these two long exact sequences as rows, and we have all these theta maps mapping them. And now I claim that this is a commutative diagram. So this diagram commutes. Okay. So one has to check that now. Wow, so should we do that? Maybe we should do it, but I don't have much space to do it because I don't want to erase these two theorems. It's nothing deep at all. You just insert the definitions, right? So let's see. So we have basically three types of blocks where we have to check it. Maybe this block, and that block. The third block here is the most interesting one because this is where this connecting homomorphism pops up. Here in the first two blocks, we basically only have inclusion maps coming up. And then you have to check that, well, so what happens? Maybe I do it more, okay? So what do? So you take an element tensor product like here. When you map it here, you just restrict to these two things. And you do nothing to the second factor. When you map downstairs, what happens? Well, this is the theta map. So what we do is, where do we have it? The general definition is, no, here it's still there. So you pull back the first factor to the total space, that's what you do. And the second factor is in a way extended. You undo this restriction map, which you can do because this restriction map was a homotopy equivalence. So that's what we do. So on the first factor, you just pull back. And on the second factor, in fact, on the second factor, you extend. And here you restrict. And the point is simply that pulling back to the total space and then restricting to these parts of the total space is the same thing as first restricting to these parts and then pulling back. Because this pullback map and the inclusion maps converge. This applies to the first block and similarly applies to the second block, same thing. And here you have to remember the definition of the connecting homomorphism, where you have to shift the degree increases by 1. And I have reminded you of the connecting map in the beginning of this discussion. Essentially, it is an extension thing and applying the differential to it. And pulling back, which you do in the theta map, pulling back to the total space commutes with taking differentials, because pulling back always commutes with taking differentials. And this is essentially the reason why this commutes also, if you write down the definition. So it's really nothing deep here. You just check by inserting the definitions and use these facts that taking exterior differentials commutes with pullbacks. So then you see that this is a commutative diagram. And now we are done, because why? We have a commutative diagram with exact rows and with arrows which are, this guy is an isomorphism, these two are an isomorphism, so this arrow is also an isomorphism. This one, this is an isomorphism, this is an isomorphism, this one we don't know. The next one is again an isomorphism, and then again an isomorphism. So you have isomorphism, isomorphism, something we don't know, isomorphism, isomorphism, and so on. And then there's this famous 5 lemma, which tells you that in this case it follows that, so if you have 2 isomorphisms to the left, 2 isomorphisms to the right, and exact rows, then it follows that the middle arrow is also an isomorphism. That's a 5 lemma, a simple algebraic fact. And then add this here. So the 5 lemma implies then that this arrow, which we don't know, is also an isomorphism. You see, this argument has really nothing to do with characteristic classes. This Leray-Hirsch theorem is an entirely topological fact, and I have set it up such that I can argue with the Majoritory sequence alone. But the theorem holds more generally without this assumption of finite time, and then you need to argue somewhat differently, but the principle, the basic idea is still the same. All right, so that's the Leray-Hirsch theorem. And now we want to use that to prove our splitting principle. This is what we are after all. Maybe I should explicitly state the corollary that in this situation where the Leray-Hirsch theorem applies, that then you have that the homology of the base manifold embeds into the homology of the total space. Let's just note that for the reference. So, under the assumptions, in the Leray-Hirsch theorem, so that you have these classes which restrict to a basis of the fibers, you have that the projection map induces an injective map from the homology of the basis to the homology of the total space. So this is injective. And this follows from this isomorphism. Why? Well, so we have this isomorphism. tensor product and the total homology of the space. Now here we have inside we have H0. And inside H0, so this might actually be disconnected. So H0 could have higher dimension. But we have something inside that, which is one-dimensional. And that's the zero class, which is represented by the constant function 1 on all connected components. So times constant function 1. That's a particular element. So this constant function 1 represents an element in here, and I take just the multiples of those. In case that Gx is connected, this is just a basis vector, right? This generates everything. But anyway, so we have that. And now here we have this isomorphism theta, and we can restrict it to this thing. So since this is one-dimensional, then we have this canonical isomorphism to H star of M, where this tensor product is just mapped to this constant times that element. And I mean, a vector space tensor R is just the vector space itself. So, and now let's see what map we get here. What's this arrow? If I restrict to the subspace, well, what happens then? Let's take a look at the definition of theta. What do we have to do? We have to take, in this case, these bases, and now one of the basis vectors in H0 I just take as this constant function 1, and everything else is ignored because I'm restricting only to this subspace. And then I have that thing represented by the constant function 1 on Gx. And I have something here, and then what I do with it, well, the second part is again mapped to the form represented by the constant function 1, and on the front part, I just pull back. So in other words, this is nothing, pull back. And so this pull back map is then just a restriction of an isomorphism, so it must be injective. So that's an isomorphism. Theta is an iso by Leray-Hirsch, therefore T star is injective. And that's what I wanted to say. And this is interesting to us because this is what we need in the splitting principle. This is the second condition. So it might be a good idea to try to find this Q in such a way that it's a principal, it's a fiber bundle over M, for which this assumption in Leray-Hirsch are satisfied. Because then condition 2 will be obtained by Leray-Hirsch. And that's what we will do, essentially. Okay, now let's prove this bit. Let's go. Okay, so what's the situation? We have a vector bundle, complex vector bundle, and we want to find a manifold Q and a map to our base manifold M, such that cohomology embeds and the pullback of the bundle splits into line bundles. And we do this proof by induction on the rank of the bundle, which is N in this case. Induction on N, which is the rank of the vector bundle. Okay, good. N equals 1. Well, there's not much to be done here, because if n is equal to 1, then f itself is already a line bundle. And then we can just take as a pi the identity in Q equal to n. Right. Just take Q equal to n, pi is the identity. Then putting back doesn't change anything, so we have a line bundle, and certainly also the homologies. There's an isomorphism of this, the identity of the homologies also intuitive. Nothing to be done here. Okay. So the interesting case comes now, it's larger than 1. And I want to do an induction, or I'm doing it by induction because then it's enough for me to split off one line bundle. And the rest will then be taken care of by induction. So that's why I'm not doing the proof directly, but I'm doing it by induction. All right. And what do we do now? How can we get to some such Q? Well, we take our bundle F and we projectivize it. That means each fiber of the bundle, which is an n-dimensional vector space, complex vector space, is replaced by its corresponding projective space. So that's one of the instances where I apply a smooth functor to a bundle to turn a bundle, in this case a vect n bundle, into some other bundle, namely a fiber bundle whose fibers are projective spaces. So let me say that. So apply the following smooth functor fiber-wise to our bundle F. Namely, it goes from the category of, let's say, n-dimensional complex vector spaces to the category of manifolds. So the result will just be a fiber bundle. And so what does it do? On objects, so it maps vector space, n-dimensional vector space, to its projective space. So to the set of all one-dimensional subspaces of that vector space, which we know is a compact manifold. It's essentially a CPN, right? So if there's a Cn, then this will be CPN minus 1. So that's what it does on objects. So that's what we apply to the fibers. And on morphisms, or rather on isomorphisms, this tells us what we do to the transition functions. So what will it do? It will also do the canonical thing. If you have an isomorphism, F, which is an isomorphism between two vector spaces, if we have such an isomorphism, we apply to it some map. So this must be now, so here the morphisms are smooth maps in this category. So we must get a smooth map from the first projective space to the second projective space. And what is this map? Must be induced by this linear map, and it's the canonically induced map, which I call P of F. And what does it do? The P of F sends a point in here, which is a line in V. So that's a line in V. It's a one-dimensional subspace of V. It must be sent to a one-dimensional subspace of W. And what can we do? There's only one thing we can do. We map this to F. Since this is an isomorphism, this will also be a line. That's what the functor does. And it's easy to see that this is a smooth functor, because then you only have to check that if you have a family of such F's which depend smoothly on the parameters, then these maps on projective spaces also depend smoothly on the parameters, which is easy to see. For instance, by looking at these maps of projective space that we have introduced. Alright, so that means this is a smooth functor. We can apply this to our vector bundle, and then we get a new bundle over the same base manifold, but now the fibers are projective spaces, namely the projective spaces of the original fibers. So obtain fiber bundle, which I might call P of F with total space or with model fiber CPN minus 1, and total space, let me call it P of E, even though this is not, it's not the projective space of E. E is not a vector space, right? E is the total space of a bundle, and this is the fiber-wise projectivization. But let me just define this as P of E. It's the total space of this projective space bundle, and let's say P of pi as projection. Okay. So that's now a new bundle, and now the fibers are compact, right? Because these projective spaces are compact. So we can see what happens if we now pull back our original bundle F to the total space of this bundle. So that's what we do next. So maybe I can erase this one. So we have a map from the total space here. So this is our first candidate of the manifold Q, the total space of this bundle. And we have a map from that to our original manifold, namely the projection of this bundle. So that's our first candidate for little p in this statement, right? And so let's see what happens if we pull back the original bundle F over M to a bundle over the P of E. So look at P pi, pull back F star, and this is now a vector bundle. So this is a vect N C bundle on P of E. Okay, so let's take a look at that. So in particular, if we look at the fiber of this bundle over some point of this new base manifold. So let's pick a point. Let L be an element here. I call it L because the total space is the disjoint union of the fibers of this projective bundle. So that means the L is an element in one projective space. So it's a line in the corresponding vector space. Okay, so let L in here. So that means L is an element of P fx for some x and n. No, because P of E is the disjoint union of these P of x's. And in fact, this x is what? Well, the x is the base point of the L under P. So that's what it is. It's the corresponding base point. So like this. Good. So it's a line. So, but it's not. Yeah, it's a line, and in fact, it's in this space. So it's a one-dimensional subspace of this one. One-dimensional subspace. But fx is the same thing as. So what happens when I pull back the bundle? I take my point L, I apply the map to it, which gives me x, and then I take the fiber of the original bundle over x. So this is actually the same thing as the fiber of the pull-back bundle of f dot over L. This is a n-dimensional vector space, and this is a one-dimensional subspace. Okay, and this works for any L, for any point L in this set P. So what have I done now? So to each point here, I have singled out a one-dimensional subspace of the corresponding fiber of the full vector. So, this family, now, let me call it tau E, which maps L to itself. L, considered as a point in here, is mapped to L as a one-dimensional subspace. This one, so this defines a one-dimensional or a rank 1 subvector bundle of the original, the pullback bundle of E star. Of course, we have seen such a construction before, so this reminds us of something. So what am I talking about here? A simple special case of this we have seen before, where we have taken L as a point, so attached to it L as a vector space and consider this as a vector bundle. The tautological bundle, yes. And indeed, if we now restrict this bundle to any of the fibers, this is exactly the corresponding tautological bundle. So we have, this line bundle that I have here restricts over each projective space, over each fiber of the projective bundle to its tautological line bundle. Because this is exactly the construction. Tau E restricts to tautological line bundle over each fiber P of Fx. So what we have done is just we take the tautological line bundles of all the fibers of my projective bundle and collect this together to a line bundle over the total space of this projective bundle. So that's what we are doing here. And this has the advantage that I have now a line bundle here, which is defined over this complete space here. And so I can take its Chern classes. It's just one Chern class. And this gives me the classes that I need in order to apply the Leray-Hirsch theorem. We put Aj equal to, now I take this bundle that I've just constructed and take its first Chern class. So this would be an element in H2 of the base manifold of this bundle, and the base manifold of this bundle is P of E, right? And then I take its jth cut product power, then this ends up in H2J. Okay? So I have there these elements, so they are elements of the total space of my projective space bundle. So see, this P of E plays two roles here. It's the total space of the bundle of projective spaces with base manifold M. But it's also the base manifold of this bundle L. And the Chern classes take their values in the cohomology of the base manifold. So because I take this tautological bundle here, so I have these classes, but now I switch viewpoint and look at the Leray-Hirsch theorem, considering the bundle, the projective bundle, and then I have these classes in the total space of this projective bundle PE. And I can apply the Leray-Hirsch theorem to that one because the A0 up to AN-1 restrict to the Chern class of the restriction of this bundle, which is just the tautological bundle of the corresponding fiber, the tautological bundle of the projective space Fx to the jth power. Right. So this bundle restricts to that bundle when I look at the inclusion map. And Chern classes are natural, so this commutes with inclusion. So this is why this restricts the Chern class of this. And restriction or pullback in general also commutes with taking this cut product. So I get this in the cohomology of this projective space. And for projective space, we know that the Chern classes and its powers form the basis of the cohomology. Right? So, and hence, two bases of this cohomology here. So that means the Leray-Hirsch theorem can be applied. This gives me the classes. It can be applied to the bundle where this is the total, space, this is the fiber, and M is the basis. So, and what does it tell us? Well, this then tells us by Leray-Hirsch and its corollary, which I have erased, that the cohomology of, so under this map from of this bundle, the cohomology embeds. So this is injected. That's what Leray-Hirsch tells us. Corollary to Leray-Hirsch. And good. That's good, because this is condition number 2. If we take Q, for our Q, the total space of this projective bundle. But now what happens to the bundle itself? Well, the bundle itself, when we pull back, so we have constructed this bundle, this line bundle, as a subvector bundle of this pullback bundle. So we have this sub bundle sitting in there, and then we can fiber-wise, so we can introduce a emission metric, for instance, and take fiber-wise the orthogonal complement. I could also write it as a quotient, but let me do it like so. So we have this splitting. After pulling back, we can split off one line. That's how we did it. It's not quite what we want, because we want to decompose it completely into line bundles. But we have split off one line. But now the induction kicks in. Because by induction, I can further split this guy. Inductive hypothesis tells me that there's another map, which I call I2 from some manifold Q to P of E, such that the pullback of this bundle, which has rank 1 less, that this can be split. And the map on homology is injected. So that's injected. That's by induction. And the only thing I have to do is now I have to compose these two maps. Right? Don't need this anymore. And so now I put pi equals 2. First, so it must be a map from Q to M. So first we map to P of E, which is pi 2. And then from P of E we map down to M, which is the projection map. Oh, it's a problem because I've used pi twice. So this, maybe I should have called this first projection map for the projective bundle pi 1. right? So the problem is I have called the projection map of the bundle f pi, and then this collides with this pi that I want to get. So if I call the projection map of f pi 1, then I have a pi 1 everywhere here. And then I have pi 1 here and call this pi, which gives me this. Alright, and then if you pull back, then it's the bundle. Then that's the same thing as pi 2 star of pi 1 star of f. So the first one gave me this decomposition into L plus L perp, which is the same thing as the decomposition of the pullback of this line, plus, and the pullback of L perp was decomposed into these lines. So I can just call this L1, and I have a decomposition into lines of my pullback bundle. So this is condition number 1. And if I look at the map on homology, then this is the same as my 2 star composed with P of pi 1 star. So as a map from the homology of the original base manifold to skew, and these two are injective. So this is by induction assumption, and this is by Leray-Hirsch. So a composition of two injective maps is injective. And this proves the first principle. So this is how it works. Now we see the construction is, so the Q is really constructed explicitly out of the bundle. It's a geometric construction. It's not just some existence fact. So that's it for today. Any questions? Because in the real case, the homology wouldn't fit. So you would have to take real projective spaces here, then the splitting thing would be okay. But the homology doesn't fit. So we don't have Leray-Hirsch. No, the Pontryagin classes are of no use because they will not generate the homology of projective space. Yeah. Mm-hmm. Yeah. And for instance, if you look at RP3, let's see. I would have to think about to what extent you can. So it does work if you take Z modulo 2 coefficients. Then things work. But here we are doing things with the round homology, then this does not work with real coefficients. Oh, the question was to what extent this carries over to real vector bundles. Typically what you do is you apply the principle, if you want to use it, you apply the principle to the complexification of your real bundles. And then you can work with it also in the real case. For example, if you want to do something with Pontryagin classes, then they are basically chain classes of the complexification. This is why that's good enough. Okay, so then that's it for today. Thank you.